Lesson 5, Applications of Sinusoidal Functions. Alright, example 1 is about the height of a person on a swing that's swinging back and forth. So we want to determine the minimum, maximum, midline, amplitude, period, range, domain, all of the stuff we normally find. So first we'll take our max point, and it is at 2, and our minimum point is at not quite at, what are these going up by? 0.25s. So if this is 0.25, this would be 0.75. It's not quite there. It's a little bit higher than that. So the minimum would be about 0.8. So our midline would be 2 plus 0.8 divided by 2, which is 2.8 over 2, which is 1.4. So at 1.4, we have our midline. That would be about right there. So not quite at 1.5, a little bit below it. But you can see that that is where the graph changes. So our amplitude would be the distance from our maximum point, subtract the midline, which is 0.6. And to find our period length, we have our maximum here, that is at 1.5. The next maximum is at 3. So 1.5 to 3 is equal to a period of 3. I mean 1.5. I don't know why I said that. So 3 minus 1.5 is equal to 1.5. You could have also gone from this maximum. You can go from any maximum point you want. You could also go from this point to this point, and I meant to put this point. It doesn't matter, but if you go from a max to a max or a min to a min, that will also get you your period length. So our domain is x such that x is an element of the real number set. And our range is y such that 0.8 is less than or equal to y, which is less than or equal to 2 for all the real numbers. Okay, part B says determine the height above the ground at 4 seconds and at 9 seconds. So at 4 seconds, oops, well, it looks like it's at about 1 meter. So 4 seconds is equal to 1 meter. Now we want to also find 9 seconds. So if we were to continue this on, we could look at the pattern. So this is at 2 and 2.5. So it goes 2 and 2.5 are at 1 meter. Then we have at 3.5 and 4. Then we have at 5 and 5.5. Then we have at 6.5 and 7. That means that our next one would be at 8.5 and 9. So if you just follow the pattern, keeping on going, we can see that 9 is in the same position as some of our other numbers. So it would be in the same spot as our 4. Just like our 4 and our 7. Keep on going and it will be at 9. So they're the same height, 1 meters. Okay, part C asks us to compare a second swing. So we're going to find all of the information from the second swing. So our max is at 2.5 right here. Our minimum is down here at 0.75. So our midline is equal to 2.5 plus 0.75 divided by 2, which is equal to 3.25 divided by 2, which is 1.625. So at 1.625, which would be in here, we have a midline. And as you can see, that makes sense to what our graph looks like. Now we're going to find our amplitude. So to find our amplitude, we take our maximum, which is 2.5. We subtract our midline, which is 1.625. And you get 0.875. You can also find your amplitude by doing it with the minimum as well. Now we're going to find our period length. So our first maximum is at 0, and our second maximum, the time when it reaches the maximum again, is at 2. So our period is 2, subtract 0, which is 2. So the period length is 2. Our domain is x such that x is an element of the real numbers, and our range is y such that 0.75 is less than or equal to y, which is less than or equal to 2.5. So now we want to compare the two swings. So first, if we look at our minimums, that's how far it gets off the ground. So our minimum on the first swinger is equal to 0.8, and our minimum on the second swinger is equal to 0.75. So from this, it's easy for us to see that the second swinger is lower to the ground. So they're lower to the ground, which means that their chain on their swing is longer. So they're lower to the ground, longer chain. Then, if we take our maximums, the first swinger is 2, the second swinger is 2.5. So this person gets higher. And the last thing that we can really look at is our period length. So the first swinger's period length is 1.5, and the second swinger is 2. So what this tells us is that the first swinger is swinging faster. They're moving faster. It takes them less time to get through a cycle, or to get through a swing on their swing. Alright, example 2. Alexis and Colin own a car and a pickup truck. They noticed that the odometer of the two vehicles gave different values for the same distance. As a part of their investigation to see the cause, they put chalk on the mark of their outer edge of the tire on each vehicle. The following graph shows the height of the tires as they rotated while the vehicles were driven at the same slow, constant speed. What can you determine about this? So first off, we're just going to know that these are inches, and across the bottom is seconds, the time in seconds. And also, if you don't know how an odometer works, I didn't either. I had to look it up. But an odometer counts how many real rotations are made, and they assume that the distance traveled is the number of wheel rotations multiplied by the tire circumference. So they take the tire circumference and they multiply it by the wheel rotations, which makes sense because when you go across a wheel an entire time, when they make the rotation, when they've gone the full length of the tire, it would be the whole circumference. This would be the distance of it rolled out. So they take however many times the wheels have turned, and they've multiplied it by that circumference of the tires. And then there's a whole bunch of other math that has to do with depending on what size the tires are. So this is what we're going to see is why the tire size is going to matter on a truck or a car. So, looking at the truck and the car, you can tell that this is the car because I'm telling you, and also because it's got smaller wheels. So we're going to find the maximum and the minimum. Our maximum is 24 and our minimum is 0, which makes sense because it has to touch the ground at some point. Our midline would be 24 plus 0 divided by 2, which is 12. So what this information tells us is, first off, that the tire has a diameter of 24. That's how big it is. It also tells us that the middle of the tire is at 12. For our second one, our maximum is at 32 and our minimum is at 0. We have our midline at 32 plus 0 divided by 2, which is 16. So again, the diameter for this is 32. The middle of the tire is at 16. That's where the axle is in the middle. We can also figure out the period length. So for our first one, our first maximum is at 0. Our second maximum is at 1.2. So our period length is 1.2 seconds. And for the truck, it starts at 0 and our next maximum is at 1.6. So our period is 1.6 seconds. So what this is telling us is that it takes less time for a car to rotate once. So that means that the car's wheels are spinning faster than the trucks are spinning in order to get the full distance of one rotation. So when the odometer is tracking the wheel rotations, what it's doing is it's noticing that the cars is clicking off more times because it's spinning more times because it's got a smaller circumference. So it will vary the odometer by a little bit. Not by a lot, but it will change the number by small amounts. We also can see the distance that each tire has gone. So the distance is circumference, which is 2 times pi times r. So for the car, it would be 2 times pi times the radius, which is 12, which would be 75.4 inches. So every rotation, they travel 75.4 inches. And for the truck, it would be 2 times pi times 16, which is 100.5 inches. So every time the wheel turns for the truck, it goes 100.5 inches, which is 25 inches more than the car.